Okay, so I recall that we have the drawing of sigma, which was isomorphic to the compactification, to the cohomology of the compactification. And so to understand the cohomology of the compactification is the same as understanding the drawing of the fan. And so you have the function which are always linear on sigma, and I said that f is a convex function. If f is a convex function, then I can associate to f an element of A, which I call a numpel element. So I denote by k the numpel elements in A1 of sigma. Okay, so now we can start to enter the heart of the subject, which is Hodge theory for fans. So I assume that sigma is a smooth quasi-projective fan. So it has at least one numpel element. And I take L any element in A1, a priori numpel, but it's not necessary. And we say that the pair sigma L verifies the Keller package if it verifies this first point, which is the Hodge-Lefschetz theorem that I will denote by HL, which is for any degree at most half of the dimension. I can take an element in AK of sigma and can multiply by a power of L to the D minus 2K, and I arrive in A D minus K of sigma. So we know that a priori, since sigma is smooth, we have Poincare duality, so both spaces are isomorphic. But now we ask this isomorphism to be given by this multiplication by a power of L. So the Hodge-Lefschetz theorem states that this multiplication is an isomorphism. So we have another things in the Keller package, but first let me just write some implications of this Hodge-Lefschetz theorem. So first, if we have an isomorphism between AK sigma and AD minus K sigma, the first multiplication must be injective because the total multiplication is injective. So we must have an injection between AK of sigma and AK plus 1 of sigma. And dually, more or less, if K is at the end, so for K at least the half of the dimension, we must have a surjection. AK of sigma must be surjective inside AK plus 1 of sigma. Okay, so more or less we have these schemes. A0 is injected in A1 by the multiplication by L, which is injected in A2, etc. And until the half, and then we have surjection. And we have a symmetry, we have an isomorphism like that. Is that clear? Okay, so in particular, we have the dimension of A0 with less than or equal to the dimension of A1, etc. So its dimension increases and then decreases. And another thing we can have with the Hodge-Lefschetz theorem is that if K is almost half the dimension, I can define the Kth primitive part to be the kernel of, instead of L to the D minus 2K, which is an isomorphism, I multiply by L once more. And so here I am surjective in this, but it's no more an isomorphism. It's just a surjection, and I define the Kth primitive part to be the kernel. So more or less, for instance, P2 is this part, which is a supplement of the image of A1. So here I have P1, etc. And so I have a decomposition. AK is the multiplication of the different primitive parts. So here I have L2 of P0, L of P1 and P2. So I have this decomposition. So the second thing I ask for a scalar package is the Hodge-Riemann bilinear relations. And so I want the pairing from AK times AK to Q, which is given by, if I have A and B, I map it to -1 to the K, the degree of A, L D minus 2KB. So this is just the isomorphism from AK to A D minus K. And then I have the Poincare duality of pairing. So by Hodge and Poincare duality, we know that this pairing is it's perfect. Yes, this pairing is perfect. And we ask it to be positive definite on pk of sigma. And so it will be positive definite on pk of sigma. It will be negative definite on pk minus 1 of sigma, positive definite on plus minus 2 of sigma, etc. So we exactly know a decomposition and the sign of the, etc. So some implication of these Hodge-Riemann bilinear relations. So first, if I take k equals 0, I just get that the degree of L to the D is positive. So since the function is convex, it's quite okay. It's it's positive. If I take k equals to 1, for instance, I can take 2 elements and the degree. So this time I don't put the -1 to the k. And so I have 2 parts. I have the part which come from P0, and the part coming from P1. So I don't have the minus, all the parts in P1 will be negative definite. And the part coming from P0 will be positive definite because it was already before multiplying by L. And so the signature of the quadratic form is 1 and dimension of A1 minus 1. So it's more or less a Hodge index theorem if you apply it to surfaces. And more generally, you can, as I said, you are positive definite on pk, negative definite on pk minus 1, etc. So you exactly know the signature of the pairing. And in fact, it's an equivalence. If you have the good signature for any AK, by induction, you can prove that, for instance, A0 is positive definite because the signature is 1, 0, etc. And so you can get back at Hodge-Riemann. So Hodge-Riemann, it's just can be, it's okay. If you know the signature, you know if you have Hodge-Riemann or not. Okay. So now I will say that a quasi-projective fan is scalar if for any ample class the pair is scalar. Verifies, I mean, the pair verifies scalar package. And so in the story, there has been several steps to prove that some fans are scalar. So first, unimodular complete fans are scalar. So I'm not sure if it's Stanley. And in fact, Stanley used this to prove the G conjecture, but I don't know if it was known before. So more or less, to prove that, you have your fan sigma, and you can associate to it CP sigma, and the drawing of sigma is isomorphic to the drawing of TP sigma, which is CP sigma, sorry, which is isomorphic to the cohomology of CP sigma. And okay, CP sigma is a projective is a projective complex variety, so it verifies the Keller package. And so this verifies the Keller package. Then, okay, so I have the same theorem. If you remember my first talk, I had the same theorem for tropicalization of complement of hyperplane arrangement. So in the same way, we can say that Bachmann fans coming from hyperplanar arrangement is scalar. But we also have some Bachmann fans which does not come from complement of hyperplanar arrangement. And this one are also scalar, which is a recent research by Achuprasito and Katz. So this has been generalized to generalized Bachmann fans, which are fans who support the support of a Bachmann fan. And with the mid, we generalize a bit more to scalable quasi-predictive fans that I will describe later. But in the classical case, any projective fan, any projective complex variety, for any projective complex variety and any ample class on it, we have the Keller package. This is not true in the tropical world. I mean, if we take our definition of smoothness, we have some smooth quasi-projective fans which are not Keller. There is a counterexample by Ian Hu, for instance. If you define smoothness to be Bachmann fans, locally Bachmann fans, of course it is always Keller because of this theorem. So this has been very studied. So Hodge theory for fans has been studied a lot because it has several consequences in combinatorics. For example, it solved a lot of conjecture, like the log concavity of the coefficients of the chromatic polynomials, if you know what it is, or the log concavity of the number of vector space of dimension k you can create with a finite family of vectors, or an entire classification of the number of k faces of simple polytopes. So you take a polytope whose faces are simplicial polytopes. Every faces is a simplex, and you wonder how many 0 faces and 1 faces and 2 faces and etc. it can have. And so the answer is okay. It's more or less described by the Turing of the corresponding fam, and so you can classify entirely this number thanks to Hodge theory. Okay, so this was for fans. So it's a very simple case. Like just me recall quickly what happened in the classical case where we have more properties. So it will be a bit, okay, it will be quick. I just want to give you an idea of the different properties we can have. So if you have a smooth projective complex variety, then first you have the Hodge decomposition. So HK can be decomposed into HPQ for P plus Q equal K if you work with complex coefficient. And you have this conjugation, HPQ conjugate is equal to HQP. So for us, HPQ is 0, SP is different from Q. So we only have the HK over 2, K over 2. With the Poincare duality, we have the Hard-Lefschetz theorem, which preserves the B degree. And we also have the Truman bilinear relations, which are a bit more complicated to state. Not really, but okay. So more or less, we have this scheme. I don't know if it's very readable. So here, for instance, we have H20, which is isomorphic to H02. So we have this symmetry. We also have this symmetry. So it's not H02, it's HT minus 2 D, which is also isomorphic to H02 via this hard left-shade theorem. And we have the complex conjugation, which gives an isomorphism, for instance, between H20 and H02. So we have all these symmetries, and this is called the Hodge diamond. And so for general tropical varieties, not only fans, we have a similar result. So, okay, I don't want to explain the details, but you can take okay, you take a tropical variety inside Rn, and you ask to be locally Keller. So locally you have fans, and you want those fans to be Keller. And so you have the recession of so for instance, if you have something like that, the recession is what you see at infinity. So it's a fan you have when you contract everything. You scale everything by 0. And so if this is a Keller fan, so not like that, maybe a tropical line, or it's a support of Keller fan, you can compactify these things into the tropical toric variety given by this. And then we have the Keller package. So the Hodge decomposition here is trivial, and it's quite interesting. Okay, so this is quite interesting. First, we have it for a coefficient for Q coefficients. This is not the case in the complex case. And secondly, in fact, in the tropical world, we can define HPQ directly, but we don't really know how to define HK differently that as a direct sum of HPQ. Maybe there is more structure you can set.
So there is no intrinsic definition of HK X if X is a tropical variety.
So we don't know.
As a cohomology of some sheaf or cohomology or complex of sheaf, there is no such thing as Hodge filtration.
No, I don't know any such thing. So
are there any conjectures, or I don't know, maybe some heuristics what this could be, or this is completely mysterious?
Not really, but yes, the idea is if you know the article of Wittenberg, Zarkov, and Mikhalkin, you want it to be more or less the HK of the tropical limit of the mixed structure, limit mixed structure. But a priori, we need more information than just what is on the tropical variety. Because, I mean, so yeah. But maybe in this case, it's not just a direct sum. We have something which is more interesting. But I don't know any way to compute directly HK without giving it at a direct sum for now. Probably we need more information, like degeneration of variety, something like that. Okay, so we still have Poincare duality. And okay, we don't have a complex conjugation because everything is real. So in fact, we have something instead of this, which is there exists a monodromy operator, which goes from HPQ to HP minus 1 Q plus 1. And in fact, this monodromy operator has the hard left-shade property. So it's a left-shade operator. If you apply it several times, you get an isomorphism between both. So we still have this isomorphism, but it's not, yes, and N is canonical on a tropical variety. L is not canonical, but N is.
There are some situations where it's known.
Sorry?
So in the tropical world, is it always a conjecture, or there are some situations where it's known that it's an isomorphism?
Here it's known. For my case, it's known. So, I mean, I think anyway, the conjecture is only a conjecture for projective variety. I'm not sure. So yes, here I wrote conjecture about the theorem. So we have the Hodge theorem. So for some Kähler class, I don't want to define Kähler class. More or less, it's locally ample. And so we have more or less the same scheme than in the complex case, instead that here it's no more complex conjugation, but it's power of n. Okay, so there are some implications. For instance, we can solve tropical Hodge conjecture in a special case, which is tropical varieties, which has a rational triangulation, things like that. Okay, so let's come back to the problem for fans. And so I stated a theorem which says that every scalable quasi-projective fan is scalar. So let me define what is scalability. So more or less the idea is that in the previous results about okay, we wanted to, in the previous result about smoothness, to prove that some fans are smooth or some fans are scalar. We work by induction more or less and use operations which preserve these properties. And so the idea is just to unpack all this transformation which preserves this property in this term of scalable. So we have some simple operations on fans which preserve scalarness. And and so if you can construct your fan thanks to these operations, you are scalar. So I need a prerequisite about tropical divisors. So we can define Minkowski weights of dimension k and sigma to be the weights. So you give to each face of dimension k a weight in Q with a property, which is this property around each face. Sorry. Around each face of dimension k minus 1. You have this sum, so more or less it's a balancing condition, right? But in a lower dimension. If you prefer, we forget every faces which are of dimension more than k, and then we put some weights which can be negative, and we want the weighted tropical fan, the weighted fan to be balanced. So we have two interesting maps. First, we have this map from Minkowski weights to the dual of the Turing, which maps a weight to the thing which maps x sigma with sigma of dimension x to just the weight of sigma. So this is well defined. And we have another natural maps, which is just what I said. So if I have a weight W, I can associate to it a tropical cycle in the compactification or in sigma itself, which is okay. For instance, I have this. I put weight 1 here, here, and here. And so I can just look at this where I put the new sigma, the canonical multivector on it. And so this is a tropical cycle. It's a cycle, so it belongs to HKK of PM of compactification of sigma, right? And actually, everything is isomorphic. If sigma is unimodular and tropical, yes. So MWK is just the dual of AK. And we have already seen that AK is the same thing as the cohomology of sigma, the compactification of sigma. And it happens that the Minkowski weights are also everything in HPM KK. So the image of this is supported on the finite cone, right? We have nothing at infinity, but it's sufficient to have all the cycles, the KK cycles. And I call the tropical divisor any element of MW d-1. So any tropical cycle of dimension d-1 of codimension 1. Okay, so a divisor, if you have a function which is canonwise linear, a priori you can define the divisor, the principal divisor associated to F, and I define it like that, which is, okay, for instance, I have my function which is 0 here, 0 here, 1 here. And for this too, I can look what's the value of F here, so it's 0. I can look what is the value of F here, it is 1. And now I can take the sum of this normal unit vector, which lives in N2, because I am balanced. And I just remove this, but here it's 0, so here the weight will be 1. Here it will be 1 also, and here I have this unit vector. This unit vector, here it will be probably 1. Here it will be 1, but I have to remove the sum of both. Okay, I'm doing some mistakes, but we get 1 here also. And so this is a divisor. So you get a principal divisor. Except that, wait, I have a minus here and a plus here, so I have to take the opposite in for everything. It's not very important. Okay, and it happens that if sigma is smooth, we have a property that is any divisor is principal. So you can take any element of any divisor, and it is the divisor of a function. And if the divisor of a function is 0, then F is linear. And the proof is very easy. It just, okay, you have, it happens that the divisor function is just, can be factorized by, okay, L sigma, we have seen that it can go into A1 of sigma. By Poincare duality, it goes into the dual of AD-1, which is isomorphic to the set of divisors. And it is factorized like that. And by Poincare duality, we know that this is an isomorphism. So the kernel of this is just the kernel of this, which is linear forms, the linear maps. So we get the theorem. Okay, now we have the divisors, and we can take the tropical modification along the divisor. So I have my function f. I denote the divisor. I assume that the divisor of f is actually a tropical fan in my sense. This means that all the weights are 0 or 1. I denote this divisor by delta, and I see it as a tropical subfan. And I take the graph of f. So to any function, to any x in the support, I map it to x and f of x. Okay, it's just a graph. So let's take an example. If this is sigma, so I just put sigma in the horizontal plane. And maybe, okay, I take the thing which is 0 here, 0 here, and -1 here. And this is a graph of sigma, right? So it has a natural structure of fans. And if I take a phase sigma here, I will call this phase sigma 0. Okay, so it's a fan, but it's not a tropical fan. It is not balanced. To make it balanced, there is a natural way to do so, which is called the tropical modification. So we call E0 the vertical ray, the vertical vector, unit vector. And for each face in the divisor, here the divisor is this, I define D, this symbol, to be the image of D by the graph, by the graph function. And I add a whole half line, vertical half line. Okay, so this is the tropicalized above D. And so I call this the tropical modification of sigma. Okay, so it looks like a bit like a blow up, like in algebraic geometry. But in fact, it's better to see it as, yeah, so first, okay, theorem, it's really a unimodular tropical fan. And there is a natural projection in the other direction. So you have to think of it more as the tropical graph, so of sigma by f. So if you take just the graph, you will not have a balanced things, but it's a tropical world. It's a bit weird, so it's natural to add these things, these vertical things. And so more or less, so what I will say is not entirely true, but it's really the idea. If you have V, which is in the complex torus, and you take a function f on V to C star to C, you have the graph of V, maybe I should call it G. You have the graph of V, which lives in TCN times C, but you can also restrict it to C star. And more or less, my F above, so my sigma will be the tropicalization of V. My F will be, if it has a meaning, I don't know if it has a meaning actually, will be the tropicalization of G. And the tropical modification of sigma along G. Okay, delta will be the tropicalization of the divisor of G. Divisor of G is zero locus of G. And this is the tropicalization of this. So it's a tropicalization of the graph. You really have to think it as a graph. And so this works particularly, okay. In general, I think this is not very well defined, etc. But it works particularly well when we work with complement of hyperplane arrangement. So if you have a hyperplane arrangement defined by lambda 1, maybe L1, etc., Ln plus 1, you have also the hyperplane arrangement A prime defined by L1, etc., Ln. And so A will just be the graph of by L plus 1 of A prime. Okay, it's a bit quick. I have to define everything, y, etc. And if you look at the divisor, so the set of the divisor of Ln plus 1, Ln plus 1 inside A, more or less it's A second, where A second is the thing which is given by L1 restricted to the kernel of Ln plus 1, etc. Ln restricted to the kernel of Ln plus 1. And so if you have the tropical modification of the Bergman fan associated to A along the Bergman fan associated to A prime along the Bergman fan associated to A second which is just a tropical modification, which is just equal to the Bellman fan associated to A. Okay, we need this later. That's why I explained this. Okay, maybe it's a bit quick. It's not really important. So you have to think it as a graph, because if you have a variety, and you take maybe a variety, and you take the graph of this function by the variety, of course the cohomology of the graph of the function is the same as the cohomology of the variety. You have then nothing. So here it's exactly the same, but we have to compactify to don't forget the divisor, etc. And so, again, the tropical word is not so true. We need sigma to be smooth for this to be true. And so if sigma is smooth, then the cohomology of the compactification of sigma is isomorphic to the cohomology of the compactification of the tropical modification of sigma along any delta, which is smooth, if delta is smooth. And so to prove this, okay, we can just work with the Turing. And so I have a tropical modification, and I denote by R the new ray. And so I have a natural map. So we have only one new ray. Okay, you have these things, and after the tropical modification, you have the same, but with a new ray above and new things here. But you have only one new ray, which is the vertical ray here, generated by E0. And so to each variable, I can just associate the corresponding variable x r0, rho 0. And so it's quite clear that it is well defined because non-faces of sigma are mapped to non-faces of the tropical modification. And if you have a linear map, it gives you an element in E2, but you can just take the pullback of the linear map by the projection. It will be the same thing. The surjectivity is just that you can rewrite x rho 0 thanks to the other ray, etc. So injectivity is more complicated, and here you will need the smoothness. And the property that any divisor is principal, etc. Okay, is that clear, the definition of tropical modification? Okay, so it's really just the graph of by a function, but it's very useful because it can change the support of the fan, and it's crucial if you want to have interesting fans. Now we have another operation we understand well, which does not change the support. So if you have a face sigma, and you take the ray rho 0 in the interior of sigma that I define like that. So you have your fan like that. I have the rays. For each ray, I have the unit vector. I just take the sum of the unit vectors, and I take the ray which goes through this sum. Now I define the blow-up of the stellar subdivision of sigma along sigma to be, I want to cut along this ray, but I want my new fan to still be simplicial. So for instance, let's say that sigma is here. Okay, so here you have a cone above, a cone below, which are of dimension 3, and there is an equatorial plane between both, which is sigma. So the ray rho 0 will be in the middle like that. And so if I want to cut here, I have to cut like that. So I will have no face and to cut below. So if I take, if you want transversally, I will see something like that. So sigma will be these things. I want to cut along this, so I have to add this and this. Okay, it's simple. Okay, there is a formal definition. It works. And so it happens that I denoted by sigma with a blow up along sigma. And so this does not change the support. Okay, it's quite clear. And it's still tropical and unimodular. Tropical because it does not change the support, and unimodular because I choose this ray, this very special way. Okay, is that clear? Okay, so we call it the blow up because Cp sigma blow up along sigma is the blow up of Tp sigma along the stratum. I have denoted this by, sorry, it's not T. Sorry, it's, I'm too used to the tropical world. Along the strata, the stratum corresponding to sigma. So in toric geometry is just a way to blow up the toric varieties corresponding to the variety. And so I call the blow down, it's the opposite operation. So if something is a blow up or something else, then in the other direction, I call it the blow down. And so this operation, we still understand quite well its behavior on the cohomology. It's a bit more complicated than before, but we have the Kills lemma. So if I do a blow up along sigma, I have a new array, rho 0, and I define T to be the minus the corresponding element in the churning. And in this case, we have this decomposition where you can see the star fans, which appears here. Okay, and so the inclusion of sigma into the blow up is you just map rho into rho if you are not in sigma. This is sigma, and otherwise you have to remove T, and you can also naturally map the churning of sigma above to the blow up.
This T dot.
Sorry?
What do you mean by TA dot? AA is the churn and TA dot is?
So here, if you have an element here, it corresponds to T times the corresponding element A. If C is that, you map it to T times that. Is that your question?
Okay.
In fact, if you want, this is yes, no, okay. It's more or less a part of A dot sigma square T quotiented by something. The usual definition is something like that. And okay, you have a natural inclusion of A dot sigma into A sigma. Okay. So here, this is just, okay, if sigma is this ray naturally corresponds to this ray, and this ray naturally corresponds to this ray. So I just map X rho prime to X rho, etc. So moreover, we know how to compute T to the sigma. And in particular, we can prove that if you have omega, which is in the top dimensional part of the churning of the sigma, then you have a correspondence between the degree of omega seen is sigma and the degree of omega, where you multiply by T to the sigma, and there is a minus between both. So we understand everything. All right, it's a bit complicated, but it's okay. And so to prove this, in fact, Kill's lemma has been proved by Kill in the, I don't know if it's for toric geometry or if it's more general, but anyway, here it's just the correspondence between the fans and their corresponding toric variety. And so the Kill's lemma applies to the blow up of this over this and you can translate back everything to the fan, and you get the combinatorial lemma. Okay. Okay, so now we can define shareability. It's exactly what I said. We have some operations and we take everything that we can obtain thanks to these operations. So we have to restrict to some tropical fans, mainly because with blowdown you can obtain things which are not unimodular or not quasi-projective if you do any blowdown. So I define unim to be the set of unimodular tropical fans, and uqproj to be the set of unimodular quasi-projective tropical fans. And so you take C equals to one or the other as you want. And we say that a fan sigma is shareable in C if first sigma is in C. And either sigma is trivial in the sense it's just the origin or just the line R with the usual fan on it. Or if sigma can be obtained from other shareable fans in C, either as a product of two shareable fans or as a blow-up or blowdown of a shareable fan, provided that the corresponding star fan is shareable, or as a tropical modification of a shareable fan, providing that the divisor is shareable. Okay, so really we take everything that we can reach from with multiplication, blow-up, blowdown, and tropical modification. So for instance, I can get this fan because, okay, I know that this is shareable. If I take the product with itself, I get this. So this is quasi-projective and unimodular, this also. And now I can just cut here. I can do a blow up here. If I want, I can do a blowdown here. So I'm just below. And then I can take a function which is 0, 0, -1. The divisor is just the tropical line. So, okay, it's shareable. I haven't proved it, but it's if from here I can take the function which is 0 here, -1 here. The divisor is shareable because it's just the origin. So I can do the tropical modification. So this is shareable. So this is shareable. So I can do the tropical modification and I get this up to some blow up. But I can do the blow ups because here the star fan is just a line or a point, etc. Okay, so we can reach many fans a priori. But can we reach any interesting fan? Yes, just before that. So why is shareable interesting? Because shareable fans are many interesting properties. First, any shareable fans, which is unimodular tropical, is smooth. And then any shareable fans in uqproj is scalar. So we can reach so many fans because we have this theorem, which is part of the birational factorization theorem. If we have two fans, which are unimodular quasi-projective and which has the same support, then we can just perform some blow-ups and some blowdowns to go from the first one to the other. Okay, so it's not trivial at all because you need to preserve quasi-projectivity and unimodularity at each time. And so it's not easy at all, but it's feasible. And actually, as I said, everything is more or less true with scar without unimodularity. And so if you go out from, if you leave the world of unimodular tropical fans, the theorem is a bit easier to prove.
Sorry, Matthieu, can I ask a question?
Yes, of course.
Did you say that the cross was a shareable fan?
The cross? No.
No.
No, okay. Sorry, it's not the cross. It's the cross, but with this one.
Okay.
Sorry, yes.
I see. Yeah, okay. Thank you.
This one.
Abramowitz and Gorthez, did they state it in those terms in terms of tropical modifications? It's just, as far as I understand, it's been a long time ago, and it was before tropical modifications.
No, I just rephrase it, but here, between this and this, there are only blowdowns and blowups.
Okay, they didn't use tropical language. It was in terms of the varieties or something. I see.
It's just easier for me to say it like that, but really just blowdown and blowups. And blowdowns and blowups have been studied for years or decades. Okay, so in particular, generalized Bergman plans are in Euclid approach, so they are shellable, so they are scalar. So why are Bergman plans, generalized Bergman plans are shellable and quasi-projective and unimodular? No, sorry. Okay, generalized Bergman plans which are unimodular and quasi-projective are shellable in Euclid approach. So to prove this, more or less, it's what I said before. It's if you have a complement of hyperplane arrangement, the corresponding Bergman plans can be constructed from two other complements of hyperplane arrangements with less hyperplanes. So we can work by induction. So this works for representable Bergman plans, but we can do the same thing for every Bergman plans. So this is to change the support, and by the previous theorem, once you have the good support, you can just get what you want just by blow up and blowdowns. Okay, so Bergman plans are shellable, so our theorem generalizes every other theorem. In particular, complete plans are generalized Bergman plans because there is a Bergman plans who supports the whole space. Okay, so more or less we have already seen the ingredients to prove the main theorem that shellable plans are in Euclid approach are scalar. So I just recall what means scalar. So for any ample L, we have the Hodge-Lefschetz theorem here, and we have the Hodge-Riemann bilinear relations. So we work in several steps. First, okay, I admit the theorem that any shellable fan is smooth. And so I recall that if sigma is smooth, then the compactification is smooth. So in particular, we get the Poincare duality for the theorem. Then, okay, it's not totally obvious, but we can work by induction and assume that any star fan is already shellable and is already working by, I mean, any non-trivial star fan for sigma different from 0, of course. Okay, we can work by induction on the dimension, etc. So the first step is to do some reduction. Okay, so by a small computation, which is not very complicated, but I will not do it here. If L is ample, so L is a convex function. If I have a convex function here, I have the star fan, for instance, at infinity here. So I have a convex function f. I can just remove from f a linear map such that f is 0 and tau. I can remove a linear map, it will not change my class L. And now I can just take the restriction of f or the quotient of f onto this. And what I mean by this is that I will get a convex function of sigma tau of infinity, which does not depend on the choice I made. And so if I have L, an ample element of K sigma, I get an element L sigma, which is ample in sigma sigma. and it happens that if L is an ample element of sigma, and if I have Hodge Riemann and so Hard-Lefschetz for any star fans which are not real, then I have Hard-Lefschetz for sigma L.
Sorry, Matthieu,
Yes.
Is it for any face, or is it you have to satisfy that for all faces?
For all faces. I mean, all rays actually, but I need for all rays.
Thanks.
Yes, I guess. And so now both things are equivalent. If there exists an ample element for which we have a Riemann, then we have a Riemann for all the ample elements. So this is more or less a consequence of this. Okay, maybe it's a bit complicated to explain. The idea is that you know that a Riemann only depends on the signature. And if you have Hard-Lefschetz, so you have Hard-Lefschetz by induction, you have Hard-Lefschetz on the whole K sigma. And this means that since K sigma is connected, you cannot change the signature. Hard-Lefschetz is a non-degeneracy property, so you cannot change the signature on K sigma. So if you have the good signature from one element of K sigma, you will have the good signature for all the elements of K sigma. So if you have Hodge Riemann for one element, you will have Hodge Riemann for all elements. So we just have to find one element now, which verifies Hodge Riemann. Okay, so the stability by product, if you have an ample element in sigma and an ample element in sigma prime, then this will, it's not hard to see that this will be ample in sigma times sigma prime. And okay, you use Kenneth formula, it's not very complicated. There is, I think, a small trick, but it's not hard. Stability by tropical modification, we have already done everything because we just have the isomorphism of the drawing. And if you have L, the pullback of L is also ample. So here we have nothing to prove, it's just direct. And the stability by blow up is just to use the Kills lemma, so it's not very easy. I can just explain quickly in a what time? Okay, I think I have the time. In the case of k equal 1, so I recall that for k equals 1, HR is just that the signature is a 1 and dimension of A1 minus 1. And so if I have a fan like that, and I blow up this fan, so I cut in the middle. So if I take the transversal cut, I see this. So before I have L, which was convex, but now it's no more convex in the new ray because it's flat. It's not strictly convex. But if I remove a bit, if I decrease a bit the value of the function here, it will become convex here. And if it's only a bit, it will stay convex as well. So if L is ample, then L plus epsilon t, t was minus x of the new ray, will be ample. Okay, now you have the A1 of the blow up can be decomposed into A1 of the old fan and T times A0 of the new fan. For the old fan, you will see exactly the same formula as before for Riemann, plus a small thing. The small thing will then not change the signature. So here you will find again the signature 1 and the remaining thing. So what we have to, it remains to see what happens for this part. And for this part, okay, you can decompose everything. Most of the, you have L sigma to the d minus sigma plus 1 is 0, because a d minus sigma plus 1 of sigma is 0. So most of the part is 0. There is part which is smaller than the rest, the remaining, and there is only one part which is interesting. And we find that L to the d minus sigma, which is positive because we have Hodge-Riemann on sigma. And this t to the sigma, but we have seen that the degree of this is minus the degree in sigma of L d minus sigma. So this is negative, and so we will have a contribution in this part. So it's okay, we have a 1 and the remaining thing. Okay, it was too fast for you to understand. I think I have no more time to explain more. Okay, so okay, so we have a Hodge theory for tropical fans and also for tropical varieties. And I think I think that with shareability is quite interesting. I think we can prove many things by shareability, by induction on shareability. Okay, so I think I will stop here.